Okay, so it's kind of become the tradition that we have, over the years, I've developed some like solar merch, okay? So if you want to buy some, purely up to you. Up there on the door are the options. So there's like long sleeve t-shirts, short sleeve t-shirts, white hoodies, blue hoodies. What I've got like a pullover, this is kind of the classier one because it has like the embroidered like logo on it. Or if you need the sweatpants, there's sweatpants over there too. So if you order some, I generally make out of that whole deal, I get about 10 bucks out of that. So anything that you order, that'll go like 10 bucks towards the total fund for your class panel or, you know, the hair dye job. So no big hurry, I just need that order a week from today. Okay, that way I know we'll get it back before Christmas. All right, so that's that. So anyway, so that's there. The order forms are on the table right beside that. So if you want that, that's what that is about. So anyway, it was kind of cool. And the solar merch is its term. Okay, so let's kind of talk about where Isaac Newton meets Kepler. So as the story goes, colleague of Newton's, they're sitting around his lab talking, and they're going, you know, we can't figure out, we know that Kepler's laws work, but we don't know why they work. And Isaac Newton, according to the legend, goes, well, it's simple. And he pulls out like a couple of pieces of paper, and it's like, well, here's why it works. And the guy says, well, why haven't you had this published? You know, what's going on? And Newton goes, well, I just didn't think it was that big a deal. So this is the short version of what happened. So you got to remember, Kepler was doing a comparison of ratios, okay? He didn't know the actual distance. So what Kepler ended up with is where Newton did the advanced form up. So let's say you want to compare the orbital period of Mars to the orbital period of Earth. Okay, so if you look at that equation, and again, this is what's going to be both orbiting the sun. So that would be big G, mass of the sun, and you'd think I'd have that memorized.
Come on, Berkey.
I know. T squared.
Here we go, dude. Are you recording? Just
Equals 4 pi squared r cubed. Okay? And so this would be period of Earth, and this would be the radius of Earth. And then that would be, no, that's Mars. It doesn't make any difference. Mars. And that would be big G, mass of the sun, period of the Earth squared equals 4 pi squared radius of Earth cubed. Okay? So if you look at it as a ratio using that big, you know, Swiss Army knife equation, well, if you look at what happens, oh, right, the G's cancel out, the mass of the sun cancels out, the 4 pi squareds cancels out, and you're just left with Kepler's law of Tm squared over Te squared equals radius of Mars cubed divided by the radius of Earth cubed. And basically Newton says, here, this is why it works. And so this is why the other reality is of why you can only compare things that orbit the same center. Because the whole key to this is that you have to drop out the mass that's at the center of the orbit. Okay? It isn't the mass of Mars, it isn't the mass of Earth, it's what's at the center of that orbit. So if you're comparing like the 4 Galilean moons of Jupiter, oh, you would have the mass of Jupiter in there, and that's what's going to drop out. So you can take Newton's laws of planetary motion and then end up with Kepler's laws as long as they orbit the same center. So anyway, there's that. So that's how those two pieces cross over. Make sure on number 10, the Lagrange points. So you should have, here's the Earth, here's the Moon, okay? You should have one Lagrange point that's inside the radius of the Moon and another point that's on the outside orbital radius of the Moon. But they both should be something times 10 to the 8th, okay? Now, to give you some, like, perspective, on that distance from the Earth to the Moon, you can take all the planets in our solar system and stack them side by side by side, and they would fit in that distance between the Earth and the Moon. Okay? So Saturn, Jupiter, all the planets you could stack right in there, and they would fit in that gap. Okay. And then also, don't forget on number 10 that to answer that last question about what happens to the velocity when the Lunar Command Module crosses L1. Okay, so when it crosses that point, what happens to the velocity, and make sure that you tell me why. You can explain it in terms of like a gravitational well. Oh, I'm over the top, I'm going to be going down the gravitational well of the Moon. You can talk about it in terms of net forces. I don't care, just there's any number of ways you can explain that. Now, on the test, I'm not going to expect you to calculate like L1, L2, okay? I'm not going to make you go through all those calculations. But I am going to expect you to know the concept, like, okay, where is the Lagrange point? Is it closer to the Moon? Is it closer to the Earth? If I'm halfway between the Earth and the Moon, which direction is the net force going to point? Those are kind of just broad ideas I'm going to expect you to know. So you're not going to have to calculate like L1, L2 on the test itself. You just need to know the concept. Okay? Anybody have anything specific you want me to work on those problems or go over? Yes, ma'am. Okay. So when you talk about escape velocity, if you visualize, if you want a visual, so imagine that you have like this gravitational well, okay? And you want to figure out basically how fast you have to throw something to get out of that gravitational well. So it's just like this on the Earth, okay? If I throw this golf ball up, okay, it comes back down. If I throw it faster, it goes farther up, okay? And the faster I throw it, the farther out it's going to go before it starts to come back down. So what that escape velocity represents is basically how fast I would have to throw this golf ball to have it completely leave the gravitational field of the Earth. Okay? If you want to send something outside of our solar system, you've got to clear this big massive star we have in the middle of our solar system. Okay? So that's kind of the visual on escape velocity. So if you look at the equation, and that's 2 big G m over r. The only difference between orbital velocity and escape velocity is that there's a 2 in there. Okay, that's the difference. So that 2 comes from kinetic energy and potential energy, which we'll get into later. So what that 2, that's the only difference in the two equations. So basically, and again, that m is the mass of what's at the center of that gravitational well. So on 19, you're talking about, well, why would it be easier to launch something out to leave our solar system from Mars than it is Earth? Well, if you like a visual, like imagine there's the sun at the bottom of the gravitational well. Well, Earth is here on the edge of that gravitational well. Mars is out here on the edge of that gravitational well. So if you like that analogy, you can go, well, Mars is further from the bottom of that well, so it's going to be easier to escape. If you like equations, the orbital radius of Mars is greater than the orbital radius of Earth, so you're dividing by a bigger number here. That makes the velocity smaller. Okay, so I don't care how people like warping, with some people like the warping in space and time, some people like the mathematical side of it. I don't care, pick one. Okay? So does that clarify that? Yeah. Okay. So on 20, basically, the idea of the simple version of black hole is they get really, really weird. Because we don't know what happens inside a black hole, because we don't deal well with infinite. And so basically what should happen is that the density inside of a black hole, the density goes to infinity, and math kind of breaks down when you talk about infinite density and weird things happen. So basically, if you go with this analogy on a black hole, and it's a really, really, really deep well, and there's a point called the event horizon. And once you cross over that event horizon, basically, you're going to get sucked into this black hole, and you get something called spaghettification, where there's enough of like a differential in the gravitational field. Like if you went feet first, your feet would get stretched out because there's such a difference in that gravitational field that we think you get stretched out over that, and because your feet would accelerate much faster than the rest of you, and it gets. But once you cross that event horizon, then basically there's no going back. And so on 20, what we're saying then is basically that escape velocity. If you set that escape velocity as the speed of light, and so okay, well, what mass do you need? So on 20, that answer should be like 10 to the 35th. So if the sun was a lot more massive, then it would be a black hole. And we think there's like a massive black hole in the center of the Milky Way galaxy, because that's kind of where everything is orbiting around. So anyway, so there's a short lesson on black holes and escape velocities. So, okay. Anything else? Hopefully what you see on number 14, that the distance to Kansas City is greater than the distance to the International Space Station. Okay, they kind of give you, then I put that on because otherwise you get a number and it's like, well, what does that number mean? And so I just put that on there so you have some kind of reference. You know, it's like, oh, okay, yeah, International Space Station is closer than it is to go to Kansas City. So, and again, we just have to be above our atmosphere to be in orbit. So, okay, anything else? Yes, ma'am.
On 17, when it talks about explain in terms of the four things, wouldn't mass and inertia stay the same? The only things that are changing are acceleration and gravitational force.
Okay, so let's talk about number 17. So here's the point, what I want you to get on number 17 is that imagine that you have Hank the bowling ball, and you've got a tennis ball, okay? And we're going to drop them both at the same time, okay? So here's Hank, here's the tennis ball. So if you wanted to calculate, if you wanted to go old school, pure old school Newton calculation, to calculate the gravitational force acting on the bowling ball, you would go F equals big G, the mass of the bowling ball, Hank, times the mass of the Earth, divided by R squared. Okay, so if you're really into calculations, like, oh man, I love calculations, okay? You could do this. Big G, mass of Hank, mass of the Earth, R squared. And then if you did Teddy the tennis ball, that would be big G, mass of the tennis ball, mass of the Earth, over R squared, okay? So notice on this that everything on here stays the same except for the mass of the tennis ball versus Hank, right? So what I want you to see is that the main thing I want you to get out of your minds is that, oh, the gravitational force is the same on everything. It's not, okay? If you have more mass, it weighs more because there's more mass to interact with the mass of the Earth, okay? So that's one thing. But what has more inertia, the tennis ball or Hank? Hank. So you have to have more force acting on Hank to get the same acceleration. That's what I want you to see on that question, okay? So they accelerate at the same rate, not because the same amount of force acts on them. That force is proportional to the mass. So if you have twice the mass, you have twice the force. But you also have twice the inertia, so you end up with the same acceleration.
Okay.
Does that make sense?
Yeah.
Okay. Bless you. All right. Anything else at all? Going once? Going twice? Okay. So here's the deal. If you want to hold on to that assignment, hand it in on Monday. That's cool. If you're done with it and you want to hand it in, that's cool too. I'll leave that completely up to you, whatever serves you best. Okay? All right. So let's review. So on the test on Monday, there's going to be two distinct parts to this test. There's going to be the centripetal motion part, and then there's going to be the gravity part. Okay? Literally. And I will tell you, oh, this test part is ended. This is where this test is going to take off. So let's start with a very, very basic idea. And this is going to be the first question on the test. I'm going to tell you this right now. When something's moving around in a circle, is it accelerating? Yes. And what is the direction of that centripetal acceleration? Inward at a 90-degree angle to the velocity vector. Okay? That's it. Okay? Don't overthink it. It's not tangent. It's not outward. Okay? It's inward at a 90-degree angle. That's it. Okay? That's the direction of your acceleration. That's the direction of your force. That's what you've got. Okay? Don't overthink it. This is going to be the first question on the test. So, is it possible, and listen to the difference between the two. Is it possible for an object to move around in a circle at constant speed? Versus, is it possible to move around in a circle with constant velocity? So can I move in a circle with constant speed? Yes. Let's start with that idea. Fu, you say yes. Why? Because the speed is just what? How fast you're going, right? So here's my point. So here's your car, okay? Actually, it's going to end up being a truck. Okay, here's the truck. I started as a car and ended up as a truck. Okay? All right? And this thing is going around in a circle. So, as this thing goes around in a circle, what can you look at to figure out the speed of your truck? The speedometer. Okay, there's a radical concept. So, you could look at your speedometer, and it would say like 10 miles per hour. Okay? So, you could drive in a circle with a constant speed of 10 miles per hour. Okay? Because that's just how fast you're going. Okay? So your speed can stay the same. But if you're moving in a circle, but are you accelerating? Yes. Because you're not changing the magnitude of the vector. What are you changing? Direction. You're changing the direction. Okay? So anytime you have a change in the direction of the vector, you're also accelerating. So now, if this truck is moving around in a circle, let's talk about this. There has to be some force that's acting inward. So what's the source of that centripetal force to keep your car or truck or whatever it is, even if you're just running? What's the source of that force? Friction. Friction. So now, if you're on a flat track and you look at mu equaling force friction over force normal, and that force friction on a flat track when you're turning has to equal your centripetal force, and that's going to be your Fg, because you're on a flat track, so your normal force is the same as your gravitational force. So that's going to be mass times your centripetal acceleration over mass over g. G's cancel out. So if you're on a flat track, okay, and you're turning, or you're on the green spinny thing, okay? So here's Polly the penguin, and Polly the penguin is sitting there on the green spinny thing, going around like this. So, is Polly the penguin accelerating? Yeah, okay? It is, because it's going around in a circle. So the source of that force is friction that's acting inward, okay? So now let's say that we're going to put Polly the penguin and Newton's apple on the green spinny thing, okay? And they're going to go around like this. Which one undergoes the greater centripetal acceleration? The penguin or the apple? Why? It's moving faster, okay? Mathematically, your centripetal acceleration equals 4 pi squared r over t squared. As they go around, do they have the same period?
Yes.
Yes, they both take the same amount of time to go around. So the one with the bigger radius has bigger centripetal acceleration, that's going to require more force, okay? So, which one's going to fly off first? The penguin, okay? Because of the fact that, sorry, so since it's further out, right, friction can only provide a certain amount of force. Once that force is exceeded, you turn into a projectile. Okay, so anytime I ask you centripetal force, centripetal acceleration, whatever, it's always acting inward. Do not make this difficult. Okay. Now, speaking of math, let's say that you have centripetal force equals mv squared over r. And let's say that I decrease the radius by 1/4. What's that going to do to my centripetal acceleration? And what's that going to do to my centripetal force? Okay, so imagine this. So here's yonder rubber stopper. And it's going around like this, okay? And this is assuming the velocity stays constant, okay? Assuming the velocity stays constant. If I reduce that radius by 1/4, okay? And now I've got it like this, okay? So if the velocity stays constant, and I reduce that velocity, that radius by 1/4, what's that going to do to my centripetal acceleration? By how much? 4, right? Because, and again, when you get a problem like this on the test, I mean, you're going to. So one option is you make up numbers. It's like, Mr. Werkamp, I'm a numbers kind of person. But I'm happy for you, okay? That's why God made calculators. So plug in 1 kilogram, plug in 1 meter per second for your velocity, plug in a radius of 1 meter. Calculate your centripetal force. Then go, oh, my radius is going to be 1/4 of that. Oh, now my radius is going to be 0.25 meters, okay? And calculate the new centripetal force. Or, if you're a math nerd, you can go, okay, that's my original centripetal force. So my new centripetal force is going to be mv squared and then r over 4. Okay? So you have 4 in the denominator of the denominator, the 4 flips up, boom, there you go. Okay? So, good with that. All right. So, let me see. I promise you I'm going to have a question on the test, and there's a problem like this on the review, where you're going to have like, I park here, you're going to have a couple of coins sitting on a spinning turntable, okay, going around like this. So when you talk about that, there's a couple of ways you can handle this. One, you could look at 2 pi r over t, and you can calculate the velocity of each one. Again, which one's going to have the greater velocity? One furthest to the outside, because it has to travel a greater distance in the same amount of time. Okay, so the one further out is going to have more velocity. I'm going to tell you that it's going to spin at a certain number of revolutions per minute. It might spin, I might say, all right, 20 revolutions per minute. Now, is that period or is that frequency? Frequency, because it's an event per unit of time. Okay, so if that's the case, then you can take 20 revolutions, divide that by 60, and that's like 1/3 revolutions per second. Okay? Now, so at this point, you can do a couple of things. Like if I ask you to calculate the velocity, so if you're old school, I want to use the period. How can you take that frequency and find that period?
1 over,
What did you say?
1 over f.
Yeah, take the inverse of it. So if you can take the inverse of that and boom, get the period. Or if you wanted to, you can also remember that you can have 2 pi r and just multiply it by the frequency. So you can either take the inverse of it and divide by the period, or you can just use 2 pi rf, boom, plug in the frequency right there. It saves you taking the inverse of it. I don't care. It makes me no difference. Just pick the one that makes the most sense for you. So then you can do the same thing with your centripetal acceleration. You can go v squared over r if you know the velocity, or you could just go 4 pi squared r over t squared, which is also 4 pi squared r times frequency squared. So here's one of the main things. Look at what you're holding constant. So if you look at those 2 quarters as they go around, that centripetal acceleration, this whole thing right here is going to stay as a constant because they're both going to take the same amount of time to go around. So if I double my radius, I double my centripetal acceleration, I double the amount of force that it takes to hold those quarters on there. Okay? Promise you, that's going to be there. Promise you. There's questions like that on the review. Okay. Now, what else is going to be there? I promise you, you're going to have questions about vertical centripetal acceleration. So that's where you're going to have a situation where you're going to have like a rubber stopper going around like this, okay, in a vertical loop, okay? That's going to be there, promise you. So what's the difference between when that stopper's at the top versus when that stopper is at the bottom? So to get the total force at the top, Ellie, do you add or subtract? Huh? Yeah. So that's going to be Fc minus Fg. And at the bottom, that's going to be Fc plus Fg. And again, don't get weird with this. Go, oh, that's it. I'm adding a negative. No, this is just, they're just all positive, okay? So here's the deal. When are you going to feel heaviest? At the bottom or at the top? Bottom. The bottom. Okay, you're always going to feel heavier at the bottom because you have to overcome the pull of gravity, so you have to provide like the normal force, and you have to provide the centripetal force to keep it moving in a circle. Now, when you're up at the top, okay, so let's see, the more complicated math happens at the top. If I want to complete the loop, okay, if I want to complete the loop, what do you know about that total force?
Positive.
Well, it could be, but it's 0, greater than or equal to 0, right? So even if at a minimum I could set this equal to 0. So if you want to calculate the minimum velocity that you have to have at the top, you're going to set this side equal to 0. Fg equals Fc, mg equals mv squared over r. Masses cancel out, you get the square root of GR, otherwise known as the K9 equation. That gives you the minimum velocity to complete that loop. So if you're going faster than that, you're good. If you're not going that fast, then that's going to happen. Okay? So that's going to get you that minimum velocity. So the other thing that's going to happen, and I promise you this, I'm going to give you a problem. I'm going to say, okay, hey, you're at the top of that loop, and you want to feel like a fraction of your force weight, okay? Let's say that you like the number 3. Okay, fine. Mr. Burkamp, I'm going to be in this roller coaster, and I want to feel 1/3 of my weight, okay? I'm a huge fan of the number 3. Cool. Nerd, but okay, let's go with it. So, remember, this is what you are going to experience. This is what you are going to feel. So you're going to sit here and go, okay, I want to feel 1/3 of my forced weight. If I said, if you're a fan of fourths, that might be 1/4. It might be 2/3. It might be 7/8. I don't know. It's just going to be a fraction. And that's going to equal FC minus FG. So the only thing that ever changes in this process is that fraction. That is the only thing that I can change. You're going to add that over, so you're going to get 4/3 FG equals force centripetal. So that's 4/3 mg equals mv squared over r. What's going to happen to the mass? Goes away. You get v equals the square root of 4/3 g. There's a problem like this on the review. Okay, it's there. The only thing I can do on this problem, okay, this is a one-trick pony. What's the only thing I can change on a problem like this? The fraction. Okay, that's it. It's like, I want you to feel a half? Do I want you to feel a third? Do I want you to feel, what do I want you to feel? Okay. Now, if you want to feel nothing, what's the fraction? If you want to be in a state of weightlessness, what fraction do you put in front of there?
0.
0. And then you end up with v equals the square root of g because you're in a state of weightlessness. Okay? So, that's just, I promise you, there's going to be a problem like this. You're also going to have one where you're going to have Bubba in a barrel. Okay? And I will literally tell you, Bubba is in a barrel. Okay? That's exactly how, when you're going to know when you get this problem, because it is going to say, Bubba is in the barrel. All right? So, here's Bubba, right? And he's going around like this. So we can model it like, here's a stopper. Okay? Put that on here. Right? So, when I go around, if I'm going fast enough, it stays there. But if I slow down, then it falls. Everybody just likes that, I don't know why. So, why does it fall when I slow down? Does gravity get stronger? No. So if you look at that dynamic, so here's this platform, okay, or here's Bubba, it doesn't make any difference. There's the stopper. What are the three forces acting on that stopper as it goes around? Yeah, centripetal force acting inward. What else? Gravity pulling down.
Friction pulling.
Yeah, you have to have some frictional force acting upward. So at a minimum, what does that frictional force have to equal?
Gravity.
Yeah, it has to equal the effects of gravity, which is pulling it down. So basically what happens is that when I slow down, what happens to the amount of centripetal force? Decreases. Okay? Because we're not going as fast. So when I'm going fast, that's like pushing your hands together really, really hard. Okay? Because that, now, when I go, I want you to listen very carefully and critique what I said. The faster I go, the harder that rubber stopper is being pushed up against the bottom of that platform. The faster I go, the harder it gets pushed. And why?
Because you're not being pushed, because nothing's pushing you anymore.
Yeah. When I'm spinning it, it's like if I spin, then I emit this magic force that pushes it up against the platform. Okay? Because if that was the case, I could spin around and then all of you would begin to feel this force. You'd go like, whoa! Okay? We can't quit spinning, all right? Whoa, we're feeling it, all right? No. Okay? But the faster I go, what happens to the amount of force it takes to make that rubber stopper move? That increases. What's providing that force? Oh, the platform is. So it takes more and more force from the platform. There's more and more of an inward force, but there's no outward force pushing it against it. The rubber stopper just wants to go in a straight line. Some people like this analogy. It's just like you're running and you're going to run into something and it's going to make you change that direction. So basically, some people like the idea that basically the rubber stopper is running into the platform, and the platform is just keeping it from going in a straight line. So, the centripetal force is going to act inward. The frictional force has to balance out the weight, because that's going to stay constant. Now, here's where this goes different. So if you look at mu equals force friction over force normal. Now in this situation, my forced friction has to equal the gravitational force that's pulling it down, okay? The normal force is is the centripetal force, because here's this wall, the centripetal force is acting inward. So that's my centripetal force, so you get mg over mac. Now, here's the difference. If I'm on a flat track, that's AC over G. If Bubba is in a barrel, it's G over AC. Okay? So keep those two things straight. And again, neither of these equations are on your equation sheet. Okay? But if you think it through, you go, oh yeah, right, going around in a circle. Yeah, friction equals my centripetal force. If Bubba is stuck up against the barrel wall, like this, okay, right? So gravity's trying to pull him down, there's some frictional force that's acting up. So visualize how that's going to be different. Okay, so one's G over AC, one's AC over G, just know which one is which. Okay, so that's going to so that portion of the test is going to be like the front 2 pages. That's going to be the first page, front and back. Okay, that's pretty much all going to be that. And I promise you, I'm going to sit, you're going to have a vertical loop, you're going to have a question with Bubba in the barrel. Okay, promise you. And it will literally say Bubba's in the barrel. Okay, all right, then there's going to be a bunch of gravity stuff, obviously. So on the gravity stuff, there's going to be questions with Kepler's third law. So you're going to have TA squared over TB squared equals RA cubed over RB cubed. Okay, and again, with this, since this is a ratio, doesn't make any difference what units it's in, because it's going to be a ratio. So, stop that for a second, let me hand out the sheet of paper. These are information on the 4 Galilean moons, Io, Europa, Ganymede, and Callisto. So let's just say that I gave you this and said, hey, you know, let's work this problem. All right, so let's just kind of go through this right quick. So you want to sketch a graph with radius on the x-axis and orbital period on the y-axis. So roughly, what's that graph going to look like? As the orbital radius gets bigger, what happens to the period of that satellite, or the period of that moon?
Increases.
It increases, right? So it's going to go something like this. And that's also true for our planets that orbit our sun. Okay? The farther out they are, the longer it takes for them to go around. Jupiter is a long way out, that takes a long time. Neptune, okay, the farther out you go, the longer it's going to take to make that orbit. Okay, so we got that. So then I say, using this data, verify that the Galilean moons obey Kepler's third law. So here's the deal. We're going to pick 2. So there's 100 different ways that you can solve this problem. So let's figure out, first off, Kelsey, pick one of the moons.
Europa.
Okay, period of Europa. Ryan, pick another one.
Callisto.
Period of Callisto. So the period of Europa squared divided by the period of Callisto squared should equal the radius of Callisto cubed and the radius of, or Europa and Callisto cubed. So there's a whole bunch of different ways that you can do this. One option is that you just put in the numbers to see if they're the same. So one option is that you go, okay, well, the period of Europa is 3.55 days squared, and the period of Callisto is 16.67 squared. And then you have the radius of Europa, which is 6.705 times 10 to the 8th cubed. And then you've got 1.8812 times 10 to the 9th cubed. Okay? So here's one thing that you could do. you can take 3.55, square that, divide that by 16.7 squared, and you're going to get a number. Okay? Now, then if you take this number and cube it and divide it by this number cubed, you should get the same number. Okay? So that's one way that you can verify it. Does this ratio here equal this ratio here? Okay? That's an option. If you're into cross multiplication, like Mr. Burkham, I'd love to cross multiply. Okay, fine. Square 3.55, multiply that by this number cubed. Square 16.67, multiply that by that number cubed. If the two numbers are equal, hey, it verifies it. If you're going to like, oh, Mr. Burkham, I like algebra problems. Cool, okay? So what you could do is act like you don't know the period of Europa. And go, oh, I'm just going to act like I don't know that. So then I'm going to cross multiply, divide by this, get this answer, see if that matches the period. Okay? Literally, there's 20 different ways you can solve this problem. I don't care. It's just whatever works for you. Okay? And it doesn't make any difference which ones you pick because they're both orbiting Jupiter. Okay? Cool with that concept. Now, here's what is going to be of vital importance. You get to that third part. Determine the mass of Jupiter from this data. Okay? And I promise you, you're going to have a problem like this on the test. So, Zach, pick one of the moons.
Europa.
Europa. Okay? So you've got the period of Europa is 3.55 days, and the radius is 6.705 times 10 to the 8th meters. So how can I take that information and find the mass of Jupiter?
GMT equals 4 pi squared r cubed.
Okay? Now, that radius, that is from the center of Jupiter out. Okay? So you don't have to add in the radius of Jupiter. The only time you would have to add in the radius of Jupiter is if I said, hey, this is the distance above the surface of Jupiter. Okay? And then you'd have to add it in. Okay? Otherwise, don't worry about it. So, if I solve this for mass, I've got 4 pi squared r cubed over gt squared. So I got 4 pi squared, and that radius is 6.705. And that's going to get cubed. Now, here's what you're going to, what are you going to do wrong on this problem?
We're not going to convert days to seconds.
You're going to leave those as days. You're going to see that, and you're blissfully going to write down days, and you think, oh, I'm doing science. Okay? The only units of time that exist are within that G, where you have the newtons, where you have kilograms meters per second squared. Okay? That's the only place where seconds exist. That's why that period has to be in seconds. Now, if you're just doing Kepler's third law, okay, and you're just doing that, leave it in days. Don't change it to seconds. Because it doesn't matter, because it's just a ratio, okay? It's like, God, don't go through all the effort. Don't. Just let it be. But anytime you're doing any calculations with big G, you have to convert everything into the MKS system. Okay, so when you see big G, think seconds. And that's the most common one that's screwed up. So, you got 3.55 days. 1 day is 24 hours. 1 hour is 3,600 seconds. Now, here's what also you're going to do wrong. You're going to be so happy about getting this. It's like, oh, I remembered what Burkham said. I changed it into seconds. Okay? And then you're going to forget to square it. Okay? Swear to God, that's what you're gonna forget to do. You're gonna forget to square it. And when you do this conversion, keep all of these seconds. Don't round this number, okay? Keep it all round when you get to the end, okay? So, what do you get?
1.90 times 10 to the 27.
1.90 times what?
10 to the 27.
That's what I got.
Still.
Now, to give you some perspective, what's the order of magnitude of the Earth? 10 to the mass of the Earth is like 10 to the 24th, right? Okay. Jupiter is 10 to the 27th. So that means Jupiter has 1,000 times more mass than the Earth does, because you have an order of magnitude of like 3 times greater. So they think if Jupiter had even like a mass of about 9 times greater, it actually would have had enough gravitational pull that would have turned into a sun and would have started the fusion process. So we could have had like 2 suns, which would be really weird. Yeah, anyway. But it's actually good that we had that, because if you look at kind of all of the things that had to go right for us to be sitting here having this conversation, there's a whole list of things. Like we have a tilted axis. Oh, great, we have seasons, right? Because imagine that if the Earth was, instead of tilted like this, let's say the Earth was tilted more like this as it went around the sun. Well, that's cool. If you're on the southern hemisphere, guess what? You're going to have 24 hours of light. If you're on this, you're going to have 24 hours of darkness. So basically you would have a hot side and you would have a cold side, okay? And the only time you would have a transition is right there along the equator. If we weren't tilted, then we wouldn't have seasons either. And we'd have the same amount of daylight every day, and it would be so boring. So we're tilted, that's kind of cool. We've got those 2 big planets of Jupiter and Saturn on the outside of our orbits. Hey, those are cool because they tend to sweep up a lot of asteroids that might come in and hit us. So it's like having 2 like big brothers on the outside kind of watching out for us in terms of like a gravitational field. We've got a moon that stabilizes our orbit. We're in the Goldilocks zone, so we're not too close where we're too hot, and we won't have oceans because all the water would evaporate. We're not too far out where we're too cold, because then all the oceans would be frozen. So if you look at everything that had to happen for us to be here having this conversation, it's pretty cool that we're here, if you think about everything that had to happen. Okay. Now, how could you figure out the orbital velocity of Io? That last question. There's 2 ways you could do it. One option is that you could go v equals 2 pi r over t. You have the orbital radius, take the time, convert that into seconds, you can do it that way. Or now that you know the mass of Jupiter, you could go v equals big Gm over r. Okay? Doesn't make any difference. Let's talk satellites. So you have a satellite a certain distance above the Earth. What's the relationship between the centripetal acceleration that it's going to experience and the gravitational value that it's going to feel? What's the relationship between those 2?
They're the same.
They're the same, okay? They're the absolute exact same. Because here's the basic idea, is that gravitational force is creating that centripetal force. That's like the recurring theme in this whole problem. Oh, mg equals mac, masses cancel out. So there's going to be a problem like this on the test, there's a problem like this on the review. This is how it's going to play out. I'm going to give you, for example, like the orbital period of that satellite, 20 hours, whatever it is. And then I'm going to say, okay, hey, figure the centripetal acceleration and figure the gravitational acceleration. So what you have to start with is that once you know that orbital period, knowing that, what are you going to find first? So let's say that takes 20 hours. and you want to end up calculating the centripetal acceleration, which is 4 pi squared r over t squared. I gave you t, so what are you going to have to find? You got to find the radius. So on the problem like this, there's one on the review, and there's one like this on the test. First thing you're going to do is you're going to find the radius. Now, how are you going to find the radius?
4 pi squared r over t squared.
Yeah. So if you look at this, because they're orbiting the Earth, go to that Swiss Army knife equation of 4 pi squared r cubed equals big G mass of the Earth times t squared. Find your orbital radius. Once you know your orbital radius, then you could plug that into there, or you could plug it into little g. I don't care, something like that. There's going to be a problem, like on that assignment, or I'm going to say, hey, I've got two identical spheres. They're separated by a certain distance apart. Find the mass of each sphere. They could be identical. I might change it up and say one has twice the mass as the other one. So if one has twice the mass and you let the smaller one have a mass of x, the other one's just going to be 2x. Okay? Promise you there's going to be a question like that. Okay, I'm done. So here's what you're going to get for the review.
Why do you get this as an option?
And I'm the test. I'm not going to, because I threw this in because it's like old school inclined plane. You have to calculate the acceleration. On the test, I'm going to give you that velocity. I put this on here to kind of get you, kind of stay current with that in terms of your eventual final. So on that one, if you just want to jump right into the acceleration that I gave you and finding the velocity, that's cool, because that's realistically how it's going to play out on the test. If you want to go through and refresh yourself on the force parallel calculations and all of that, you can do it that way. I don't care. What's actually going to be on the test is going to be what happens when it hits the loop. So just keep that in mind. Number 6, this is this big question with Bubba in the barrel. Okay, what's going to happen through all of that? On the gravity side of it, there's Kepler's laws to start with, and then like this question number 16, if I say the satellite has an orbital period of 3 hours, what is the centripetal acceleration? So this last question on the review is what we had just talked about. Here's the only thing that's going to happen on the test. I'm going to change that from 3 hours to 12 hours or something like that. Okay? Process is going to be the same. All right? Now, historically, not just, this is just a statement of fact. Historically, this test is the lowest test average of all the tests. Okay? So, if you're thinking about whether or not to study, you might. Okay? And again, you have everything back. Okay? You have every assignment back. You have every lab that's back. Go through them. Okay? Say, ooh, look at this. Like, God, I don't remember how to do that one. Better work that one again. Okay? Or if you look at like, wow, I tanked that assignment. Wow, probably ought to figure out what went south there. So, anyway, again, this is what I would do. I would take the blank one, and I would treat it like the test. And I'd try and work it. Then, I'd go to this to see how you do. Because if you start with this, and you go, oh yeah, that's exactly how I would have worked that problem. Man, Burkamp is spot on. Okay, wow. God, you think you taught this class before, you know? So, that's just, you know, something to think about. All right, I am done. So,